In electronics, when describing a voltage or current step function, rise time is the time taken by a signal to change from a specified low value to a specified high value. These values may be expressed as ratios or, equivalently, as percentages respect to a given reference value. In analog or digital electronics, these percentages are commonly the 10% and 90% of the output step height. However, other values are commonly used. For applications in control theory, according to Levine, rise time is defined as the time required for the response to rise from X% to Y% of its final value, with 0% to 100% rise time common for underdamped second-order systems, 5% to 95% for critically damped and 10% to 90% for overdamped ones. According to Orweiler, the term rise time applies to either positive or negative step response, even if a displayed negative excursion is popularly termed fall time. Overview. Rise time is an analog parameter of fundamental importance in high-speed electronics, since it is a measure of the ability of a circuit to respond to fast input signals. Many efforts over the years have been made to reduce the rise times of generators, analog and digital circuits, measuring and data transmission equipment, focused on the research of faster electron devices and on techniques of reduction of stray circuit parameters. For applications outside the realm of high-speed electronics, long rise times are sometimes desirable. Examples are the dimming of a light, where a longer rise time results, amongst other things, in a longer life for the bulb, or in the control of analog signals by digital ones by means of an analog switch, where a longer rise time means lower capacitive feed-through, and thus lower coupling noise to the controlled analog signal lines. Factors affecting rise time for a given system output. Its rise time depend both on the rise time of input signal and on the characteristics of the system. For example, rise time values in a resistive circuit are primarily due to stray capacitance and inductance in the circuit, because every circuit has not only resistance, but also capacitance and inductance. A delay in voltage and/or current at the load is apparent until the steady state is reached. In a pure RC circuit, the output rise time is approximately equal to 2.2 RC. Alternative definitions. Other definitions of rise time, apart from the one given by the Federal Standard 1037C and its slight generalization given by Levine, are occasionally used. These alternative definitions differ respect to the standard one not only for the reference levels considered, for example, the time interval graphically corresponding to the intercept points of the tangent drawn through the 50% point of the step function responses, occasionally used. Another definition, introduced by Elmore, uses some concepts from statistics and probability theory. Considering a step response V, he redefines the delay time Td as the first moment of its first derivative V, i.e. Finally, he defines the rise time Tr by using the second moment rise time of model systems. Notation. All notations and assumptions required for the analysis are listed here. Following Levine, we define X% as the percentage low value and Y% the percentage high value respect to a reference value of the signal whose rise time is to be estimated. T1 is the time at which the output of the system under analysis is at the X% of its the steady state value, while T2 the one at which it is at the Y%, both measured in seconds. Tr is the rise time of the analyzed system, measured in seconds. By definition, FL is the lower cutoff frequency of the analyzed system, measured in Hz. FH is higher cutoff frequency of the analyzed system, measured in Hz. H is the impulse response of the analyzed system in the time domain. H is the frequency response of the analyzed system in the frequency domain. The bandwidth is defined as, and since the lower cutoff frequency FL is usually several decades lower than the higher cutoff frequency FH, all systems analyzed here have a frequency response which extends to zero. Thus, exactly For the sake of simplicity, all systems analyzed in their simple examples of calculation of rise time section are unity-gain electrical networks, and all signals are thought as voltages. The input is a step function of E0 volts, and this implies that zeta is the damping ratio and omega 0 is the natural frequency of a given second-order system. Simple examples of calculation of rise time. The aim of this section is the calculation of rise time of step response for some simple systems. Gaussian response system. A system is said to have a Gaussian response if it is characterized by the following frequency response, where sigma equals 0 is a constant related to the high cutoff frequency by the following relation. Even if this kind frequency response is not realizable by a causal filter, its usefulness lies in the fact that behavior of a cascade connection of first-order low-pass filters approaches the behavior of this system more and more closely as the number of cascaded stages asymptotically rises to infinity. The corresponding impulse response can be calculated using the inverse Fourier transform of the shown frequency response, applying directly the definition of step response. To determine the 10% to 90% rise time of the system, it is necessary to solve for time the two following equations. By using known properties of the error function, the value t equals t1 equals t2 is found. Since tr equals t2, t1 equals 2t, and finally one-stage low-pass RC network. For a simple one-stage low-pass RC network, the 10% to 90% rise time is proportional to the network time constant tau equals RC. The proportionality constant can be derived from the knowledge of the step response of the network to a unit step function input signal of V0 amplitude. Solving for time, and finally, since T1 and T2 are such that solving these equations we find the analytical expression for T1 and T2. The rise time is therefore proportional to the time constant. Now, noting that then and since the high-frequency cutoff is equal to the bandwidth, finally note that, if the 20% to 80% rise time is considered instead, TR becomes one-stage low-pass LR network. Even for a simple one-stage low-pass RL network, the 10% to 90% rise time is proportional to the network time constant tau equals LR. The formal proof of this assertion proceed exactly as shown in the previous section. The only difference between the final expressions for the rise time is due to the difference in the expressions for the time constant tau of the two different circuits, leading in the present case to the following result: rise time of damped second-order systems according to Levine. For overdamped systems used in control theory, rise time is commonly defined as the time for a waveform to go from 0% to 100% of its final value. Accordingly, the rise time from 0 to 100% of an overdamped second-order system has the following form. The quadratic approximation for normalized rise time for a second-order system, step response, no zeros, is where zeta is the damping ratio and omega 0 is the natural frequency of the network. Rise time of cascaded blocks. Consider a system composed by n cascaded non-interacting blocks, each having a rise time tri I equals 1 n, and no overshoot in their step response. Suppose also that the input signal of the first block has a rise time whose value is TRS. Then its output signal has a rise time TR0 equal to, according to Valley and Wallman. This result is a consequence of the central limit theorem and was proved by Wallman. However, a detailed analysis of the problem is presented by Petit and McCorta, who also credit Elmore as the first one to prove the previous formula on a somewhat rigorous basis.